Hello friends, in this video we are going to study about the time response analysis of the second order control system when the input is a unit impulse function. So let's start with our topic. So in this topic, we are going to find out the output response of a second order control system when we have applied the input as a unit impulse function. Now we know that the transfer function of a second order control system, it is given by the expression So this is the transfer function of a second order control system. You can see that the highest power of s in the denominator polynomial, it is 2. So this is a second order control system. Now if we multiply this rs to the right hand side, it will become cs equals to okay. Now this Rs, it is the Laplace transform of the input, and Cs, it is the Laplace transform of the output, because when we see the block diagram, the Cs will be the Ct will be the output for a second order control system. If we see, this is the transfer function, or we can say Gs, and this is Cs, this is Rs, or we can say that this is the input signal Rt and this is Ct. Okay, so this is the Laplace transform of output and this is the Laplace transform of input, and this is our transfer function. Now if we know the input signal, here we have to find out the time response analysis when the input is unit impulse function. So this Rt, it will be the unit impulse function, or we can say that Rt is equals to del t. Del is the unit impulse function. So if we find out the Rs, that is the Laplace transform of this signal, then we can put the value of Rs here, and then we can take the inverse Laplace transform of Cs so that we can get Ct. Okay, and Ct will be the time response, or we can say the output response of the system. So we are going to find out the Laplace transform of this signal Rt, which will be Rs equals to 1. Okay, when we take the Laplace transform of unit impulse function, it is 1. And then we are going to put this value in this expression, and then we will simplify it. Okay, so our next step will be Cs equal to Rs is 1, and then the transfer function is omega n square upon s square plus 2 del omega ns plus omega n square. Now we are going to simplify it. We are going to convert it in the form of standard formulas of inverse Laplace transform, so that we can directly apply the formulas here and can get Ct. Okay, so here we are going to do, this is omega n square, so we are going to multiply and divide this expression by omega n under root of 1 minus del square, and also we are going to simplify this denominator term. So just multiplying it with omega n under root of 1 minus del square and dividing it with omega n under root of 1 minus del square. Then this term is same, omega n square. Now if we add and subtract plus del square omega n square from this polynomial, there will be no effect, okay, because we are adding and subtracting same term. Now if we see this s square 2 del omega ns, and this del square omega n square. It is forming the a plus b square formula. So we can write s plus del omega n whole square, and from the remaining terms we can take omega n square common. So we have omega n square, and remaining terms left are, here we are left with 1 and here we are left with del square. Okay, so these three terms, they are forming this a plus b square, and from the remaining terms we have taken omega n square common, and we are left with 1 minus del square. Okay, now subtracting this omega n and this omega n square, so one omega n can be cancelled out. So now we are left with, put this omega n here, and then we have under root of 1 minus del square here. This omega n is left here, and this under root of 1 minus del square we can also take here, and the denominator polynomial, this as it is. We can write it as omega n under root of 1 minus del square whole square. Okay, omega n under root of 1 minus del square and whole square is there, and then this is as it is, s plus del omega n square, and here we have omega n, this under root of 1 minus del square, and this omega n is written here. So now we are going to take the inverse Laplace transform of this expression. So inverse Laplace transform of Cs will be Ct, and this omega n upon under root of 1 minus del square, it is a constant term, so it will be as it is, and this is the making the formula of e raised to the power minus at, and then we have sine of, this is omega square plus a square. Okay, so we can have it here. We can apply this inverse Laplace transform formula directly. So we are going to get Ct equals to omega n upon under root of 1 minus del square e raised to the power minus del omega nt, and then sine okay. So this is sine omega t and e raised to the power minus a t. Now this is the time response of a second order control system when the input was unit impulse function. So this is the final expression for the output response which we have obtained. So this is the output response equation. We can write it here. Output response of a second order control system for a unit impulse function. Now we are going to take different values of del. We are going to consider that for different values of del, what will be the output response. So our first case is for del less than 1. Now when del is less than 1, if we see this output response equation, we can see that it has an exponential term, and this exponential is decaying exponential. That is, the exponential is having a negative sign here. So this will be a decaying exponential. That means it will be decreasing with time. So when the case is that for del is less than 1, the output will have decaying exponential oscillations with time. Okay, that means it is going to have oscillations which are decaying with time. So we can write it here. that for del is less than 1, response will have decaying exponential oscillations with time. Okay, so this was the case when del is less than 1. Now we will consider the second case when del is equals to 1. So for del equals to 1, we are going to put the limits del tends to 1 on this output response equation. So our output response equation is this, what we have obtained. So let's write it here. We will apply the limits del tends to 1 on this output equation. Now we will multiply and divide this expression by t omega n. So if we multiply it by t omega n, then this is omega n upon under root of 1 minus del square. We are also dividing it with t omega n, and this term is as it is. Now we will put this omega n under root of 1 minus del square here. This will become omega n square. And this t omega n under root of 1 minus del square, we are going to put it here. Now, if we apply this limits del tends to 1 on this sine term, then this sine theta will tends to theta, because when we apply that this limit del tends to 1 on this sine term, then it is going to approach towards theta. So this theta will become Ct equals to limit del tends to 1 t omega n square e raised to the power minus del omega n t, and this is becoming omega n under root of 1 minus del square t, and this can be cancelled with this, because if we apply the limits del tends to 1 on sine theta, it will become theta. So this will be going to cancelled with this. Okay, so this term is neglected. Now we are left with only this term. Okay, so when we apply the limits del tends to 1, so this will become e raised to the power 1, means it is going to become 1. Okay, and we are left with only t omega n square e raised to the power minus del omega nt. So we can see that this Ct, the output response, it is depending upon this term omega n, because del is becoming 1. So we are left with only t omega n square e raised to the power minus omega n t. So we can say that when del is equals to 1, for del equals to 1, the output response depends upon omega n. Okay, so we can write it here. For del equals to 1, response depends upon omega n. Now we are going to take the third value for del, that for del greater than 1. We have considered del less than 1, del equals to 1 we have also considered. Now we will take del greater than 1. So for del greater than 1, we have the output response equation once again the same, omega n upon under root of 1 minus del square. This was our output response equation. Now if del is greater than 1, so this will be del is greater than 1, so it has to be del square minus 1. So we can take minus sign common from this. So it is going to become under root of minus sign has been taken as common. So we are left with del square minus 1. And here we have from here also we can take minus sign common. So minus del square minus 1 and this is t. Now this minus sign, because we know that j square is equals to minus 1. So we can write it at in place of this minus 1 we can write j square, and in place of this minus 1 we can write j square. Okay, so we can write it here ct equals to omega n upon under root of j square del square minus 1 . Now this j square, it is under this under root. So when we take it out, it will become j. So this is ct equals to omega n upon j under root of del square minus 1. And here we have sine omega n j under root of del square minus 1 t. Now this is omega n j. This is an imaginary term, so it can be converted into omega n upon j under root of del square minus 1. This will become sine of h and this j will come out. Okay, so j and this will become sine h and theta will be as it is. Now this j and this j, it can be cancelled out. Okay, so we are left with the terms omega n upon under root of 1 under root of del square minus 1, and here we have sine of h omega n under root of del square minus 1 t. So if we expand this, if we have this formula that for sine h theta, it can be written as e raised to the power x minus e raised to the power minus x by 2. We have the formula for it. So we can apply it here. You can write ct equals to omega n upon under root of del square minus 1. Here we were having del omega n t, and this will become e raised to the power under root of del square minus 1 omega n t minus e raised to the power minus by 2. So we have written e raised to the power x minus e raised to the power minus x by 2. Now this e and e, they can be multiplied inside. So we can get ct equals to omega n upon this 2 is written here. If we multiply this, we will get e raised to the power minus del omega nt, they can be taken as common. So we are left with del plus under root of del square minus 1 omega nt minus e raised to the power. We have minus this, and this is also minus, so we can take minus sign common. So this is the output response when del is greater than 1. So we have got the equations for the output response for different values of del. First we taken the condition that for del is less than 1, for del greater than 1, and then del equals to 1. The three conditions we have taken. So in this video, we studied about the time response analysis of a second order control system when the input is unit impulse function. First, we consider the generalized form of the transfer function, and then we applied the input, which is unit impulse, and we take the Laplace transform, which was Rs equals to 1. Then we put the value of Rs in that formula, and then we taken the simplified it, taken the inverse Laplace transform, and we got the output response Ct for the second order control system. So I hope that this video is clear to you. Thank you.